Hello and welcome to the Earth Science Research Group seminar at the University of Liverpool. Today we're delighted to have a talk from Lisa McNeill. Lisa is a professor of tectonics at the National Oceanography Centre at the University of Southampton. Lisa specialises in the active tectonics of subduction zones and continental rifts and their associated geohazards. Prior to attaining her professorship at Southampton, Lisa completed her PhD at Oregon State University in the USA and also worked as a Royal Society Dorothy Hodgkin Fellow at both the University of Leeds and the University of Southampton. Lisa has also been extensively involved in the International Ocean Discovery Programme and has co-led various drilling projects to investigate the properties of faults and sediments at rifts and subduction zones. In this seminar, Lisa is going to talk to us about one of her ongoing projects in the Sumatra Sunda subduction zone and present the findings from a recent drilling expedition.
Many subduction zone processes basically are influenced by the materials that are input into them. So those input materials are going to help affect fault properties, in particular the frictional behavior, fluid production and permeability. And in addition, we've had, I say recent, I probably should update that now because we're now talking about sort of 15 or so years ago, but relatively recent large plate boundary subduction earthquakes have been a little bit more unusual than we expected. We sort of traditionally think that the slip rupture zone is going to be deeper down within the subduction zone. We had a couple of examples, first of all with Sumatra in 2004, and then even more so Tohoku Oki in 2011, where slip was shallower and potentially even to the trench in some cases. And in fact, earthquake sequences seem to support that idea that even those shallowest parts of the subduction zone can potentially be seismogenic. So this obviously has implications for the sort of magnitude of earthquakes and tsunamis, so it's important to understand why. And so particularly in the case of Sumatra, we started thinking, a number of us started thinking about what role very thick input sections might play. And I'm talking here about, several kilometers, and those particularly associated with submarine fans. And maybe there's something about these materials, and particularly their sort of thermal properties and diagenesis that can lead to maybe greater potential for this shallow and hence wider rupture. But also thinking about why does the plate boundary fault or the décollement form where it does, and how do those input properties then affect the fault slip? So one of the other problems we have, although there's been a lot of ocean drilling of subduction zones, including their inputs, there hadn't really been very much drilling of this particular type of sort of very thick, large submarine fan inputs. Not surprisingly, really, because they're very thick, and therefore to actually reach your target of interest, it's very challenging, so you have to drill deep. So following the 2004 earthquake, the northern part of the Sunda subduction zone, so sort of offshore North Sumatra and beyond, as well as other parts of the margin, has really been a big target of marine geophysical surveys and shallow sampling. And that included actually a consortium in the UK that Andreas Rietbroek in Liverpool was involved in with us as well. And now from 2016, we've also been able to do some IODP drilling. So we've gained a huge amount of knowledge about this particular margin, building on what was known before. And so finally, sort of a secondary part of what we were doing was that we were drilling part of the major Bengal fan system, and actually a very undersampled part of it. And so this has significance for how that the biggest submarine fan on the planet has evolved, and also it's an archive of Himalayan uplift and monsoon activity through time as well. So I'll tell you a bit about that too. Okay, so just a couple of sort of bit more information about what might control earthquake slip behavior on the plate boundary. So as I said, we tended to think that the shallowest part was made of unconsolidated sediments, and that wouldn't undergo seismogenic slip, so it would behave aseismically. And the seismogenic zone itself would be more in the sort of 10 to 40 kilometer kind of depth range. And that the updip limit of that would be controlled by temperature, which in turn has effects on mineral diagenesis, which then controls frictional behavior. That's something that obviously Dan's an expert on. And that includes, dehydration of clays. And so obviously all this also depends on the composition of your input materials. And then the down dip limit, which is something that we really can't access by drilling, is going to be likely controlled by temperature and or maybe contact with the mantle wedge if it's serpentinized. And there's been various sort of models for the sort of patchiness and heterogeneity of how slip might occur on the plate boundary. So these two earthquakes that I mentioned that have happened in relatively recent times, this just shows you a bit more information about the evidence for shallower slip. So on the left, we've got the Sumatra Andaman 2004 event, and there were various different slip models generated following the earthquake, not surprisingly, from seismological and geodetic data. And this is just one example, but it shows that the areas of high slip are in red and orange. And it shows that there's quite a number of patches in the sort of the outermost part of the subduction zone that seem to have high slip. And then even more obviously in the Tohoku Oki example, there's very clear evidence that that slip did propagate all the way to the trench in the area of very high slip. So a number of sort of put together various sort of ideas as to why that might be in both cases. So in the case of Sumatra, we started to think about the fact that we're going to be generating high temperatures at the base of these very thick inputs. Your diagenetic processes are probably quite advanced, and maybe that can be strengthening the plate boundary. You know, basically some of the processes that would go on normally in the subduction zone are happening before you even get there. But in the case of Tohoku, where they were actually able to drill and sample what's probably the plate boundary fault, there they think the large shallow slip is differently linked to a weak clay. So actually quite a different hypothesis, but leading to, in some ways, the same result. So let's sort of focus on the Sunda subduction zone and then zoom in on this northern part of Sumatra. So prior to drilling, we had also sort of had a look at how the structure of this subduction zone varies along strike. So both in terms of sort of the internal structure and also its morphology. And it really is highly variable. This image is just showing you the bathymetry of the seafloor. It's a very long subduction zone. It's not surprising that it varies. But parameters such as the width of the prism and the slope of the prism, as well as the structural style of the faults within the prism, are quite variable. And some of those changes are gradual, and some of them are quite abrupt. So that then sort of makes you start thinking about segmentation of the subduction zone and maybe how it might relate to earthquake processes too. So one factor we've already alluded to is the sediment input, and generally that thick sediment input thins from north to south, but there are some deviations from that, and in a large part they're due to the 90 East Ridge, where you can see this northeast shallow sort of volcanic ridge that impinges on the subduction zone. So although we've got really high thicknesses in the north, they then kind of shallow over that ridge, and that obviously has had some control on the transport of sediment down into the Nicobar fan. But then we pick up again the thick sediments, and then it sort of gradually becomes thinner and certainly more variable. And so we start to see some correlations between the sort of input sediment thickness and the structure. And I just highlighted again, you know, that there had been huge amounts of study done on this margin, not too much marine geophysical data, and as I said, no drilling actually directly related to the subduction zone. Sorry, these are very, very tiny little figures. Those were just on the left, showing you pretty much just a line drawing of the seafloor bathymetry, just so you can see the different structure as we go from north to south, and the width of the accretionary prism itself. So you can see generally you've got this sort of trend of the prism width decreasing from north to south, and you can see that actually on the right as well in B. But it's not actually a gradual process. There is some abrupt changes. So that's an example there where the prism width quite abruptly narrows. And it actually coincides with this boundary between the 2004 earthquake, and then a few months later there was another earthquake in 2005. So we've got this sort of structural change coinciding with an earthquake segment boundary. But the other thing I wanted to draw attention to, if you look on the left at profiles D and E, you can see that the prism actually offshore North Sumatra has got this really strange kind of plateau shape. So it's very wide, but it also forms a plateau rather than your traditional kind of taper of a prism. So there's something unusual there, and we conjectured that that was probably going to be related in some way to material properties, either internally or at the base of the prism. So just coming back to the right again, yeah, this was just sort of a summary of some of those results. We've got prism slope versus prism width, which commonly shows a correlation. I've kind of highlighted a little bit how the prism width seems to actually make quite a sharp change as we go across this earthquake rupture boundary or segment boundary. And then at the bottom, we've also got some kind of correlation between prism width and trench sediment thickness. The question mark dot is one which I can explain, as in explain why it's off the trend. So there's a bit of a trend there. And overall, when we look more closely, we found that the prism morphology does seem to be connected to sediment thickness, but also some elements of basement topography. And you probably do need some kind of element of sediment and or basement properties as well, so not just the thickness. So that was a study that we did before we did the drilling. I had mentioned the 2005 earthquake, so just to show you, zooming in on the margin so we can see where that segment boundary is located. So that's on this island of Simalu, and this is where there's quite a change in the morphology and structure of the margin, and this is the boundary between these two earthquakes. And these two earthquakes behaved a little bit differently as well. So we've just talked about the 2004 earthquake having quite a lot of evidence for fairly shallow slip, so slip underneath the prism. And actually in this bathymetry image, you can also see this sort of really quite strange plateau of the prism that doesn't continue to the south. But in terms of also the slip during the 2005 earthquake, this was more sort of typical of what we had expected before, where the slip was a bit deeper down and more sort of concentrated beneath the forearc high and the forearc basin. So contrast there. So this next, oh sorry, that's just summarizing the changes in sediment thickness. So this kind of summarizes those differences across between northern Sumatra, which is part of the 2004 rupture, and central Sumatra, which is the 2005 rupture. So we've got differences in the character of the seismogenic slip, as in where it's located. Something I haven't mentioned is where the décollement is located and its properties. We've actually got a sort of fairly strong seismic reflection in the input section in 2004 that appears to form the plate boundary fault. There's poor evidence for that in 2005, and possibly the plate boundary is actually more at the sediment basement interface there. We've got this difference in the structure and shape of the prism. We've got this unusual plateau versus a more normal prism. We've got differences in the input section, so very thick to becoming quite a lot thinner and more variable. And another point I didn't make as well, which is that we've got some seismic velocity information, and there's actually quite a contrast even in addition to these differences in sediment thickness. We've got very high velocities at the base of the inputs offshore 2004, but much lower offshore 2005. So quite a lot of differences there that might all be linked together. But what we really lacked was ground truth. So we'll be coming to that in a moment. Just a bit of seismic data. The top profile is not brilliant, but it's showing you, again, a little bit more information of the forearc. So you can see this very wide sort of plateau prism, and then you can see the forearc basin behind it. And then the lower profile kind of tags on to the western end of that upper profile and shows you the incoming input section. And so just to point out a few things in that lower seismic profile, you can see the thicknesses. This is in time, but I can tell you that at the trench, we're talking about a thickness of about 5 kilometers. And that the décollement, which we think is where that sort of red horizon is located, is at about 4.5 kilometers depth. So it's fairly deep in the sediments, but not quite at the basement. And we're reasonably confident of that. However, we do have some alternatives for where the décollement might be as well. It's not absolutely black and white as we have in some subduction zones, I would definitely add. You can see the really rapidly deposited trench wedge that's completely filled, or almost completely filled. And then if you track back to the west, you can see we go a very long way until we reach our borehole site. So site U1480 is one of our drill sites, and it's basically more than 200 kilometers from the deformation front. But unfortunately, that's where we had to go to be able to reach basement. so there's a lot of extrapolation here. So bear with us, but we didn't really have too much choice. The other thing that's worth noting again is the 90 East Ridge, and that clearly, and we'll see that does have some influence on what we're sampling at these borehole sites, which we do need to consider may not be completely representative of what's being subducted at the moment. Okay, so this is from a study by Jakob Geersen and some of the rest of us in Southampton, and this just kind of brings together some of these ideas about the seismic properties of what we think is the reflector that develops into the décollement, and then some of these ideas around the diagenetic processes that might be going on. So we've got a reflector that has seismic polarity that suggests that it's actually got high pore fluid pressure. So we think that there's fluid being generated and trapped within that reflector. We think that that's a plane of potential weakness, which can, help for the fault initiation to occur there. But then those reflection properties disappear when we get into the subduction zone, which suggests that those fluids are then released. And in general, you're sitting at the base of a section that's probably developed high temperatures. It's reached the temperatures where some of these, particularly sort of clay diagenesis processes have occurred, things like smectite to illite. So we've changed the kind of frictional properties of the material as well. And so by the time we reach the accretionary prism, we've got material that's sort of frictionally stronger, and therefore could potentially accommodate this shallow earthquake rupture, and maybe can also explain this kind of unusual prism structure as well. Okay, so we'll get more into that with some ground truthing from the drilling. Eventually we get to the drilling. Okay. So in 2016, we drilled at 2 sites, and you'll notice, so these are the red dots that you can see here in the red box. So they are pretty far from the subduction zone, and I explained one of the reasons for that is that we needed to be far to actually reach, get the full sequence, or the deeper part of the sequence that would be hosting the plate boundary fault. We had hoped to drill closer to the subduction zone as well, to sample at least the trench wedge and just get a feeling for what was going on there too, although that's probably less significant for the properties of the subduction zone. But unfortunately, we were not able to get permission to do that because that's in Indonesian waters. So part of what our strategy here is we're basically in international waters, so we were kind of pushed there, and then we had some operational challenges which I'll show you in a moment, which led to some changes too. But anyway, we've ended up with a full sequence that's been sampled, and also able to log the entire borehole, which is quite amazing. So of our objectives, which were to look at these initial properties within the input section, and then use those to try and sort of project and see how they would evolve as they approach the subduction zone and get incorporated into the subduction zone. We were able to do that, and we're now obviously working on the results in terms of what are those properties, how will they evolve, and how do they affect these different processes. We were also able to get this full stratigraphic sequence of the Nicobar fan, which is great. First time that's been done, and being able to compare it with the rest of the Bengal fan. So you can see there's various other borehole sites around the area, but there was nothing really other than these more distal southeastern sites that really were sampling the Nicobar fan. So we can kind of put those into that general picture, as well as looking at Himalayan uplift and climate history. We weren't able to unfortunately do this last part, which was hoping to maybe get another site where we could look at sort of variability in stress field in the incoming plate, because this is an area where the biggest, I think this is the biggest intraplate earthquake occurred in 2012, the magnitude greater than 8 within the oceanic plate. So we wanted to kind of see what's going on there, and is there anything from drilling we can hope to gain. But unfortunately, due to our technical challenge, we were not able to do that. So this just shows you, again, the sites relative to the subduction zone, quite far away. And then closer to, you can see the sites. And you might also say, well, why did you drill 2 sites that are so close to each other after all of that? Again, it wasn't ideal, and a lot of it was sort of down to where you could get permission to drill. It was sort of being sort of shoved further west and getting closer to the 90 East Ridge, and also availability of seismic lines as well. But it was a test to see how representative. Our main site was U1480, which we sort of sampled completely and did some logging. So it's partly sort of to see how representative that was, and I think that is a good test. You know, sometimes it is a problem if you've just got one site and you presume that that's completely representative. So it's nice to be able to get some sampling of somewhere, even if it's not that far away, just to sort of test that hypothesis. And that second site was where we were able to fully log, and that was an advantage because it's a site that we had not been open for so long. Because we only partly cored it, and therefore we had much greater chance of being able to log it. And we did indeed, pretty much pulling out the tools as the whole thing was collapsing behind us, but we managed. What you can also see is the channel that's between these 2 sites, that is the Nicobar Channel, which is sort of the most recent sort of feeder on the Nicobar fan. This shows you again that same seismic line, and really just for context, so that you can see the stratigraphy. The red parts are channels, the black faults. It's quite a heavily faulted section, and again that's important to think in terms of what role do they play in terms of either trapping fluids or releasing fluids. And again you can see where the site is located, or the primary site, U1480. And we'll come back to this when we look at the sedimentology at the end. So this was the crew and scientists on board. So we sailed from Colombo to Singapore, and then we popped into Singapore again, and then came back again, and then back to Singapore. Some people on board looking at some of the cores. And some more people also looking at the cores. You might know Paola on the right, Vanuki. Some of the cores were quite beautiful, and I'll show you some more images. The upper part of the sequence is primarily this sort of Nicobar fan, kind of greyish muds and sands. But then when we got down into the sort of deeper pelagic sequence, including quite a lot of volcanoclastic and igneous rocks, there's some really quite sort of beautiful cores. This was the challenge we had. So we were kind of 2/3 of the way through the expedition, and there are 2 main breaks, and these are really pretty sizable things, as you can see. This is actually just one of them. So on the left is the old one, and on the right is the new one. But there are 2 of these, and they basically hold the drill string, which is kind of important, and particularly here because we were in about 4 kilometers of water, plus we were drilling to nearly 1.5 kilometers below the seafloor. So we've got a lot of drill string. So you really need to have some control on it and not drop it. So unfortunately, we were sort of 2/3 of the way in, and one of these breaks failed. And it had to be replaced. So we basically had to drive to Singapore and get a spare. And it's not, luckily there was a spare. To be honest, now I can't actually remember the entire story, but the ship had been refitted in a shipyard in Singapore a number of years ago. And so they actually returned there and were able to, they pretty much did have something on hand that they could use. So anyway, it took us 11 days of sailing, fitting, and then coming back again. But it could have been worse. It could have been the end of the expedition. Okay, so what did we achieve overall? So we had these two sites. We were able to drill the full sedimentary sequence down to basement, the basaltic basement, and also to log that entire section. So the sort of entire coring was at the first site, U1480, and then the sort of full logging was at the other site, but we can correlate the 2 with some partial coring in the second site, and also using the seismic data that we have. It was quite challenging, not only because of that technical issue I mentioned, but we were drilling a lot of sand. It was quite amazing when you think about how far away you are from the source here. So we're mostly talking about Himalayan source sediments, thousands of kilometers away. There's still quite a lot of sand and, you know, relatively coarse materials. So that was challenging. And because they were deep holes, we had to case the holes, and that obviously takes time. considering the materials, particularly the sand, the recovery was not bad actually. So 54% is pretty good considering what we were coring. May not sound good to you, but that's not bad. And because of the sort of seismic data and then the logging, we were then able to kind of integrate all of those data sets and link the two sites. So in spite of some of those gaps in the coring, we were able to do that. So this is UF1 1480 again. We've seen these seismic lines, but just to zoom in at the bottom so that you can see where the site is located. And I should note that prior to drilling, we had made some interpretations as to where we thought the base of the fan sediments were and where the pelagic sediments were. And actually we were wrong. It was a little bit deeper, and it turns out that our kind of candidate for the décollement, the plate boundary fault, is actually this boundary between the main fan sediments and the pelagic sediments. So it's quite an important and significant stratigraphic boundary, which is where this is being formed. That just shows you what we did. Lots of holes, including various stabs to try and actually get started at the beginning. So this is the stratigraphy, and as I said before, we've got this upper sequence, which is our units 1 and 2, which is the sort of main part of the Nicobar fan. So those are late Miocene to recent sediments, so about 9 to 10 million years to present. And they're interbedded clay, silt, sand, and some ash. So we've got some tephra chronology we can do as well. And very high sediment accumulation rates, and we'll come on to those a little bit later. And then the deeper section is late Cretaceous to late Miocene, pelagic, hemipelagic, volcaniclastic, lava flows, and intrusions, which are probably related to 90s ridge. And we definitely see an increased state of lithification here, and also an increased clay and volcaniclastic content here. This is a sort of a beautiful array showing you the sort of the range of cores and facies. It's actually set out quite nicely in this paper by Kevin Pickering and Hugo Pouderou, focusing on the facies, but it kind of broadly relates to the units as well. So the upper sort of parts, and on the left, the grey bits basically, are the Nicobar fan deposits. Overlying those is F and J, and they are actually fairly sort of low activity fan, so much more sort of carbonate biogenic sediments. And then below those, we've then got the sort of unit 3 to 5 sort of pelagic mudstones and carbonates, which you can see. So some beautiful white carbonates, but then, yeah, actually I'm going to just sound really stupid and non-sedimentological. Anyway, nice colours. So, and then that's accentuated even more when we get sort of deeper into the section. You start to see more of these volcaniclastics and sort of beautiful sort of oranges and some conglomerates. So really nice. And then some of these igneous intrusions, which you can see at the top, H3. And then something else that was really quite exciting, we basically cored through a log, essentially. We've called it a large piece of wood, but probably what we're talking about were two, horizontally lying trees. so really, you can't quite, you can just about see the scale here. So they were sort of 10 to 15 centimeters thick pieces of wood. And these are angiosperm conifer, and they're sitting at about 850 meters below seafloor. So we think these are, so the late Miocene age. And we think it's the largest wood sample in scientific ocean drilling, which we thought was quite exciting. I'd put these in as extra slides to show you the cores, but I think I'm going to whip through those because I'm talking far too much. So obviously we've got physical properties from the cores as well. And this just highlights some of those. And I think the main two things to point out are that you've got quite a contrast at the main unit boundaries, the lithostratigraphic unit boundaries, particularly as we go down from unit 2 into 3, from the fan into the sort of more pelagic materials. You can also see the velocity increasing, as well as sort of compositional changes. And then the other thing to point out, if you look at the chloride and silica from the pore waters and the porosity, you can see that down in sort of unit 3, there's something a bit odd going on, some deviation. So we'll come back to that in a moment when we talk about diagenesis. And then the second site that we drilled at 1481, not too far away, It's lacking those sort of igneous and volcaniclastics, so we're a little bit away from the influence of 90 East Ridge, which is good. But generally, it does sort of support the idea that 1480 is more or less representative, but we've maybe got an example here where we've got less of that 90 East Ridge influence. And so you can see on the left kind of what we sampled. So the deeper part was cored from 1150 to 1500 meters below seafloor, but then we logged the whole thing. Just. And these are some of the logging data in the lower part of the hole. And again, they show, but more clearly and in some more detail, because we've obviously got sort of the recovery problem with the cores. So we've got, again, those contrasts at the unit 2-3 boundary that you can see at the base. And you can see some details of the compositional logs as well. And this really is important for our correlations, as I said, but also being able to make a solid correlation using the sonic data, which required a lot of work, but really helped to make the correlation with the seismic data and to really think about the sort of time depth conversion. So again, yes, we're seeing in the lower part, the deeper part, the pelagic part, more homogeneous, higher velocity, more lithified, fits with the cores, and then sort of a change in composition as well. So onto the geochemistry that I just mentioned. So you noticed that there was this chloride change in the deeper part of the section. So this is often looked out for and linked to freshening, so generation of fresh water, often linked to diagenesis and dehydration. And so what we're seeing here is we've got our sort of chloride value, and then it drops when we get into this distinctive layer within unit 3. And there's also an increase in amorphous silica at the same location, and also an increase in porosity too. And you can see some of this material in the right in a slide. So what was found was this is an interval of some quite altered, hydrated, so initially hydrated and altered volcanic material, which is now dehydrating, or that's our interpretation. So this was sort of amorphous silica, or otherwise interpreted as pelagonite within these pelagic mudstones. So we found we've got this interval, and it seems to sit quite nicely with where the seismic horizon further towards the subduction zone becomes this sort of anomalous polarity interval where maybe there's fluid being generated. But one question you might ask is, but hang on a minute, if this is all sort of volcanics, is this all coming from 90 East Ridge? Is this really representative? And that's a good question, so I'm putting that out there already. There are other, you'll see that there's more work that's been done on the general composition of the materials beyond just this volcaniclastic material. So what was done, there's 2 studies I'm about to show you, one by Andre Hoipers and one more recently by Duncan Stevens, a PhD student. And what they did was basically thermal modelling to try and sort of model this sort of chemical process and see what the dehydration process is and what projecting to the subduction zone. And so in addition to just sort of modelling those temperatures, we did actually have some in situ temperature measurements. We'd hoped to get more, but managed to bend one of the probes very nicely. You can see the bottom left. We did get some temperature measurements. And then there are also heat flux measurements, which again, Duncan in his later study was able to kind of compare with his modelling and try to match. So we have some shallow direct temperature measurements that we can use to ground truth some of these models. But yeah, difficult to use the probe. We broke it. Okay, so this is Andre's study, which was done fairly soon, like pretty much on the ship. So he was one of the geochemists, and he basically worked on the data that I showed before, and then did some sort of fairly quick thermal modelling of the different materials and how they might behave in terms of their dehydration as the temperatures increased. So in the bottom panel, you can see how temperature would change with time. And just as a marker, our kind of 0 is sitting at where site U 1480 is. So he's kind of doing most of his modelling around the site, and then off to the right in both time in the future from the site, but also distance as in getting closer to the subduction zone. What you're seeing is then a projection of the diagenetic processes that will happen as those temperatures increase, as they get buried more deeply. And so you're seeing the fluid production from these processes. And he's got both the opal A to CT to quartz process that's going on, and also the smectite to illite process, which is standing in here for a kind of a proxy for palagonite, because there really isn't much known about how that would behave. And then you've also got fluid that would be generated from compaction. So summing some of that up, it's lots of curves going all over the place, but what you can see is at 1480, the modelling suggests you would be starting to get the beginnings of this dehydration process, which fits with the chloride anomaly. And then if you look ahead to the subduction zone, it looks as if the majority of that dehydration process would have occurred. The opal process is starting before the smectite, but in both cases they are well underway by the time you reach the subduction zone. So it supports this idea that those fluids have been generated and potentially later then released, resulting ultimately in a sort of dehydrated, stronger section that could promote this shallow slip. But I'll show you a bit more detail from Duncan's work. So Duncan did more with sort of linking the borehole data with the seismic data and the thermal modelling. So he did more analysis of the sort of temporal history using the seismic stratigraphic interpretation and using more borehole parameters, so age and lithology and clay composition and thermal properties, but also looking at the porosity in more detail, the velocity for the time depth conversion. He also looked at, are you getting a temperature contribution from radiogenic clay? The answer was probably not very much. And he also tried to fit this heating effect that you might get from some of these slightly younger igneous intrusions that we had found at the borehole to try and match the heat flux measurements at the seafloor, and that worked pretty well. So he was trying to make a match, more of a match to the heat flux data that are existing at the surface. So that thermal rejuvenation that you can see in the top left is representing that intrusion that happened about 10 million years after basement formation. So the left-hand panel is showing you the temperature progression with time. So you've got panels starting at 9.3 million years, which is about the start of the sort of main Nicobar fan deposition. And then you're just looking at different panels through time through to the present day. And then the reflector R11 is the one that is this pelagic fan stratigraphic boundary, the one that we think is developing into the décollement. So that's the one to kind of look at. And so we can see in the present day, not surprisingly, the sediments build up through time and the temperature increases at the depth. And we can see that R11 is sitting in that bottom panel, the present day panel, in the sort of temperature range of, getting on for about sort of 130 degrees. So that's the sort of temperatures it's reached in the trench. And then on the right, just as an example of one of these dehydration reactions, he's showing you the fluid being generated by the smectite dehydration process, and again through time. So what you can see, the panel D at 1 million years ago, you can see that actually there's quite a lot of fluid being directly generated, so it's in purple, where this R11 reflector is. And actually when we get to the present day, that's pretty much finished, and now the fluid's being generated above that reflector. So again, that kind of fits well with the sort of this timing of that process being pretty much done at the depth of this reflector of interest. Okay, and just, yes, the R11 polarity reversed, that's the interval where we've got this negative polarity reflector that suggests there's fluids trapped within this interval. And again, that fits quite well with most of the fluids being generated, at least in the last million years or so. So that fits quite well as well. And sorry, there's far too much text and too much going on this one. But just to sort of sum up a few things, what it's showing is the orange is showing you the temperature. So we saw that from Andre's work, and Duncan did a similar thing here. So you've got the temperature scale on the left, and the orange is showing how that temperature increases from the borehole to the subduction zone on the right. And so there it's reaching this about 130 or so degrees at the deformation front. And then you've got the three main sources of fluid generation. So we've got compaction, smectite dehydration, and amorphous silica dehydration. And so you can see their various contributions, and the sort of, again, how they're developing as you approach the subduction zone and with time as well. And you can see that I mean, actually, there's more than enough fluid. So quite a lot of that fluid must have been lost, and probably these faults that we looked at are playing a role there in the sort of more distal part of the section and in the shallower part of the section. But he found that just even in the last million years, there's the sort of the right amount of fluid that can explain that negative polarity reflector near the deformation front if it's trapped in a layer that's about 70 to 80 meters thick and about 30% porosity, which kind of fits with both the sort of seismic and sort of drilling sort of parameters. So we also think that cementation is probably playing a role here in sort of firstly trapping those fluids around this kind of stratigraphic boundary where we've got this sort of probable décollement developing. So that's probably going to play an added role in sort of reducing the effective stress because of the trapping of the fluids there and helping to initiate the décollement. But in addition, it's then going to be sort of strengthening that section as it gets incorporated into the subduction zone as well. So overall, there's a good match between the ground truth data from drilling, the seismic and the heat flux observations, and the modelling results here. And we're getting a bit more detail than Andre's initial study. And they support that the décollement ultimately ends up being well drained, materials are dehydrated and those fluids have generally dissipated, and then it can be positioned within sort of frictionally strong materials, which can explain the sort of shallow seismogenic slip, and also probably gives an explanation of why it's forming where it does, i.e. it is a plane of weakness where fluids are being trapped. Okay, so that's enough on that. And just to finish, just some slides about the Nicobar, the Bengal Nicobar fan system. So as I said, the drill holes that we had were basically rare sites on the Nicobar part of this bigger Bengal Nicobar fan system, which you can see on the left-hand map. So most people tend to sort of know of the Bengal fan, and we feel the Nicobar fan part east of the 90s Ridge is a bit neglected. And also we shouldn't forget that a large part of this material is already accreted into the subduction zone as well. So there's a history there in the Four-Arc Islands that people studied in the 70s and 80s as well. So we've got this sort of complete, the first sampling, the full section of the Nicobar fan. So I'm just going to show you a few slides about how we've kind of worked that into the sort of Bengal fan system history, and looking at some of the really high sediment accumulation rates here. So that's what this slide is about. It's sort of, again, quite a lot of stuff going on here, but really you just want to look at the gradients of these graphs and the numbers in italics, because what we're showing here is a sort of age depth plot, but it's showing you the sedimentation rates or the sediment accumulation rates. So the left-hand image is purely from site U1480, so that's our main site. And then the right-hand image has got our two Nicobar fan drill sites, but it's also got two Bengal fan sites. And they're actually, in terms of position with distance north-south, they kind of straddle our sites. So one of them's a bit north and one of them's a bit south. So what we see, and hopefully you can see this, at about 9 to 10 million years, we see this major increase in sediment accumulation rates. So the numbers in italics are shifting from about 15 to 27 to about 200 to ultimately more than 300. So these are in meters per million years, just to get your head around the numbers. So this marks the onset of major Nicobar fan deposition. There has been some deposition going on before that, but at a much, much lower rate. And those rates, particularly you can see that 362, they're equal to, or in some cases exceeding, the Bengal fan rates that we've got in the same interval at these other drill sites on the other side of the 90s Ridge. So it's just as significant, and it sometimes maybe exceeded their significance. That rate then decreases at about 2 million years, and it looks as if this Nicobar Channel that I pointed out in the bathymetry is probably inactive from about 300,000 years ago. And so we've got this really, this obviously helps to show that we've got this really thick sediment section that we've just been talking about that comes into the subduction zone. So people did some provenance analysis on the materials. So on the left, you've got some data from detrital zircon ages, and on the right, some strontium neodymium. So that was work mainly on the left by Andy Carter and Kevin Pickering at UCL, and on the right by Wenhuang Chen, who was on the expedition as well. But they broadly agree that the data indicated we've got an eastern Himalayan source, primarily carried by the Paleo-Brahmaputra River, and it matches quite well the Andaman Nicobar Islands, which are kind of part of the forearc, which initially were derived from the Indo-Burman range to the north. And the timing of this sort of kick in sedimentation rate fits really quite nicely with some of the sort of rapid exhumation in these parts of the Himalayas, particularly the Shillong Plateau and the Surma Group. So both that sort of kick around 9 million years, but also another one that's around 3.5 to 2.5 million years, which fits quite nicely. So you've got increased exhumation and erosion. You've then also got sort of reduced accommodation space on the continent, partly also because the Burman ranges are kind of shifting westward. And so it's kind of driving things south offshore. And then we'll sort of have a look at how that works with the whole system. So this is then looking at the sort of interplay between the Nicobar and the Bengal fan. And we'll see in the next diagram kind of a map of, you know, which one's sort of dominating, and how we can start to look at sort of the submarine fan development too. So we've got the Nicobar fan at the bottom in red, the Bengal fan in green, which seems to sort of start its sedimentation more before the Nicobar fan, but then when the Nicobar fan takes off, it's actually got sort of higher rates. So there's a bit of a sort of trade-off, some overlap in their activity, but generally you can see things sort of switching between them. And then the 90s ridge, which is obviously the shallow ridge, basement ridge, is still picking up a signature of this. And this is probably from the sort of the shallow, this is where my obviously sediment gravity flow knowledge is not great, but the sort of shallow elements, the sort of fine-grained shallow elements of these flows are still being deposited and captured on the 90s ridge. And actually that's kind of showing both records. So you're kind of seeing a more continuous record there. So this, I think, is hopefully the final slide. It's a sort of a series of maps through time, just showing how we've had this sort of switch between both parts of the sort of Bengal and Nicobar fan receiving sediment, and a bit more domination by the Nicobar fan in the kind of at about 9 million years. A bit more of a kick in sort of uplift and erosion and flux around 3.5 to 2.5 million years, and then a switch back to the Bengal fan dominating in the last couple of million years, which is probably, some of these effects are probably related to things like sort of channel lobe avulsion and switching from side to side, but also we've got the 90s ridge, which is now sort of impinging on the subduction zone, which is sort of limiting the flow of sediments that can go down to the east to the Nicobar fan. So we've probably seen the end of that. So nonetheless, though, the Nicobar fan is a significant sink of Himalayan-derived material, particularly in this 9 to 2 million year period. And we've got this sort of combination of, you know, enhanced erosion from tectonic uplift, maybe an element of monsoon strengthening too, coupled with channel avulsion in the submarine fan switching from west to east. And so rather than sort of a pattern of gradual progradation, you've got sort of quite sort of punctuated, abrupt changes as tectonics and climate interact with the fan system development. Okay, I think I'll stop there. I'm not going to read these because time's dragging on, but those are my conclusions and a few insights into what we've learned from drilling some deep holes. Okay, I'll leave it there.
That's great.